Okay, folks, our last topic for the semester, correlation and linear regression. This will correspond to assignment 2930. Again, it's a double assignment, so that'll make it worth 24 points. There's only 2 questions, but they have multiple parts as you're about to see. So if you would, again, hit pause anytime you want and get caught up with things. If you would look at question number 1. So we have somebody collected data from 6 students. In reality, you probably collect more data points than this. But again, just to keep the idea relatively manageable here. And here's the idea. So somebody, for example, this first line of the table is we had a student who had 0 hours of absence throughout the semester, and they ended up with a 94% in the course. So these are the number of hours that the person missed class, and this is the eventual course percentage. So the question is, would there be a correlation between these 2 variables? Not only that, but in elementary statistics, we're asking the question of whether there's a linear correlation. So I want to remind you, and I hope you would recall this on your own, if somebody were to ask you, what do you remember from college algebra about linear relationships between 2 variables? I hope you remember that equation y equals mx plus b. All right, and that's what we're working towards. We're asking, would a line be a suitable model for that data? So to get things started here, a visual that we will do, and we've already identified that the hours of absence, we're going to call that x, and we're going to call the course percentage y. And so, we could have a big discussion about why that would be, but time is of the essence. One of the things we'll do is we'll create what's called a scatter plot, just to get a visual. So we treat each of these observations as if it's an ordered pair like we did back in algebra, x, y. So on this graph paper over here, we know the x-axis and the y-axis from our college algebra days. So a scatter plot for this, just to get a visual going, would be, all right, when x is 0, y is 94. And again, just get in the ballpark. We're just trying to get a rough visual of this. This observation, a person had 2 hours of absence and they ended up with an 88% in the class. Again, it might be off scale a little bit, but you get the general idea. And then 3 hours of absence, 92% in the class. So we're plotting each line in the table as if it was an ordered pair, like we did back in college algebra. So 5 pairs with 75. Person had 5 hours of absence, ended up with a 75% in the class. 6 hours of absence, 68% in the class. And again, I might not be getting these perfect. On the scatter plot that I'm asking you to do, just get close, all right? If we had really good graph paper up here, and then we had a person with 8 hours of absence and they ended up with a 42% in the class. All right, so hopefully what you're seeing would be that as the absences go up, the grade's coming down. I mentioned earlier that we had each line on the table represented a particular student. We have 6 data points. 6 data points. All right, so what are the general relationships that we might see from this particular thing? Well, I hope you would agree that this seems to be in a downward trend with a negative slope, a line with a negative slope. Now, those aren't perfectly in line with each other, but the general trend seems to be centered around that line. That line seems to be kind of run down the middle of it. And that line would have a negative slope. So that'd be an example of what we would call a negative linear relationship. We also could have a positive linear relationship. And I have links to these, which I believe I have to now get out of this. This is just kind of one of those deals I got to do. So just wouldn't a general picture of a negative linear slope look, something like that, a line with a negative slope. And then, of course, if our scatter plot looked more like this, that would give us a positive linear slope, a line with a general positive upward trend, positive slope. And then, but other things could happen. For example, if your scatter plot looked something like this, they call that curvilinear. all right? It's not a line. I've always thought that was a strange term, curvilinear. But you might recall from algebra, parabola, quadratic, parabolic. Those could be other patterns. What I need to mention to you then is that in this class, we're only investigating whether the data appears to be linear. All right, and so it could be maybe one of these other types that is essentially not linear. It's got a curve to it. All right, and then there also could be, from that scatter plot, maybe there's no relationship at all. In other words, maybe the two variables don't really create a discernible pattern. Maybe it's just scattered all over the place, and we would consider the two to be independent of each other, where there's no correlation whatsoever between the two variables. And that again would be considered a no relationship at all, just completely independent. Now, just looking at it, this appears like there might be a suitable mathematical model. So that's the question we're about to answer. Is a line a suitable model for that data? And it appears like it might be. So we don't just look at the picture though and go, yeah, that looks like a negative linear. We don't just look at it and go, yeah, it looks good enough to me. The scientific way to do it is we determine what's called correlation, and you have all these notes, so we can go through this a little quicker because you don't have to stop and write things down. Have these notes handy if you would, all right? But the question we're about to ask would be, are these two variables, according to the stats nerds, linearly related, all right? And if so, how strong is that relationship? We are about to determine what is called a correlation coefficient. It's called R. And what I would tell you would be that an R value, I'm going to put that picture down here, an R value falls anywhere between -1 and +1. It always will. And it's a formula we're about to take a look at. And all R values fall between -1 and +1. And the general interpretations of R values, which by the way we take to 3 decimal places, would be this. The closer we are to -1, the closer the R value is towards -1, that would indicate a negative linear relationship. So the closer you are to -1, the closer you're going to have an R value, a correlation coefficient in the vicinity of -1. If it's closer to +1, then that would indicate a positive linear relationship, positive linear, a line with a positive slope. And so the closer you are towards those extremities, the more linear you are. All right? So what number would not be linear? 0. See, if you deviate from those extremities, the less linear you become. So again, if the data were to plot as a curvilinear they call it, then you'd be in the vicinity of 0. You're not linear at all. Likewise, if there's no relationship at all, the less linear you are, the more your R value will be towards 0. So keep in mind that an R value of 0 essentially means that you're not a linear relationship. All right, so the closer you are, the closer the R value to -1, the more linear you are in the negative direction. The closer you are to +1, positive linear, and in the vicinity of 0, you're not linear at all. That's the idea there. So, you're probably wondering, how do you find the R value? R. Long John solvers. R. Let's find the R value. Well, a correlation coefficient, R, is, first of all, here we go. These 6 students constitute a sample, the small circle. The big circle would be the theoretical all students. The correlation coefficient from a sample is called R. R. And it's a formula that will appear on the screen here momentarily. I can't wait. And then the corresponding parameter, which would be the theoretical correlation for all students, is called the Greek letter rho. And again, you can see it on the screen, you can see it on your printout. So again, this is in keeping with everything we've talked about. A statistic comes from a sample. So these 6 students, these 6 data points would be a sample that we can get an R value for. And then the rho, the Greek letter there, would be the theoretical, what would the correlation be for all students? Okay, what is the formula for this? You already have it in front of you, so it kind of takes away the fun. But there's your R formula there, and that's where everybody goes, ooh, that is so cool, isn't it? Okay, so there's our formula. Now, you notice a bunch of sigmas here. So we've talked extensively that whenever we see a sigma, the thing to do would be to make a column. This is in keeping with what we've seen before. Now, I will tell you that the table we're about to make is also within your materials. I think it's the next slide. Well, it's slide number 3. So I'll go through and talk it through on this one, but I would like to think that you could duplicate this very quickly. So we see sigma xy, sigma xy. So let's make a column called xy, and I'm making this one in green if you can't tell, and my green marker's not the best here, so let me hopefully be able to find a better green one. So you take x times y, 0 times 94 is 0, 2 times 88 is 176, this is mechanical, 3 times 92 is 276, I did the math ahead of time, 5 times 75 is 375, 6 times 68 is 408, it's just number crunching, isn't it? All right, and then 8 times 42 is 336. And then we're going to add up that column, and again, I'll point out that's xy added up. All right, so that particular column is 1,571. This is mechanical arithmetic. I've been doing it this way for a long time. Former students have told me, it's cool, I understand. Keep it rolling, all right? Sigma x, I just go through here and find all the sigmas. Wouldn't that be to add up the x column? So the sum of the x column is 24. All right, and then we have a sum of y in our formula. That would be to add up the original y column, which is 459. These are all the types of things we did when we did standard deviations and variances, where we had a table and we squared things and things of that nature. All right, you also notice this formula has a sigma x squared in it, down here on the bottom. Look at it in front of you. So we make another column where we add up, where we square all the x's. And I'm putting this in red. You'll see why in a minute. So 0 squared is 0, and 2 squared is 4, and 3 squared is 9, and 5 squared is 25, and 6 squared is 36, and 8 squared is 64, and then we will add those up. And again, that would be square each x, and then add it up. So that column adds up to 138. We've already got the sigma x. I'm just going through one by one and finding all those summation notations so that we can get our R value. All right. Later on, here's a sigma y squared. You need to square all the y values. We need to take the column that's been labeled y and go through and square all those numbers. I'm doing this one in blue. Square all the y values. 94 squared is 8836. 88 squared is 7744. 92 squared is 8464. You get the idea. Go through and square each y value. 5625, 4624. It's just mechanical stuff, isn't it? And then 1764. And then add that column up. Because again, sigma y squared. I know it's hard to see, but look at the bigger version of it that you're holding in front of you. And so then that column adds up to 37,057. So I built this one on the board. Probably what we'll do when we get to example 2 is we'll just go, okay, do the same thing we did on example 1, where you go through and create those columns. Now, you probably won't be able to see it on the screen up here, but I believe in your materials you will see, will this please take me where I want to go? Why is it not working here? It's freezing on me. Let me maybe go back to a different view here. All right, I believe in your materials you see a slide that's got this basic table here with the green, red, and blue columns as we just built together on the board. All right, so in the interest of board space, whenever we need to go back to this, I will say, go look at that. And we'll pull the relevant numbers from this. So this is going to be interesting because we're going to have the formula. Typically I have all kinds of board space. I need to erase, replace. There's your table that was just built. That green column's kind of hard to read, but keep in mind it had 1571 on the bottom. Okay, so I've got to erase this. And from that table and that formula we were just looking at, we can now determine the R value. So keep this table in front of you. I am going to put the formula for R back on the screen, and I will reference these various columns as we put the numbers in their appropriate spots. Sounds like a plan? Okay, I hope so. So, there's your table. It's in your materials. I think I looked at it. I thought it was pretty legible. But here we go. We're going back to the formula now for R. And we have N. Well, N would be the fact that we had 6 data points. There were 6 values, 6 lines in the table, if you recall. Again, keep that table in front of you. I'm looking at a version of it right here in front of me. All right. Let's see. Sigma xy. Wouldn't that be the sum of that green column? I think so. So that would be 1571. Go back to the table we just built. I had to erase it to make room. Okay? Minus, let's see, in that formula, sigma x, that'd be just the very first sum of the x column, which was 24. All right, and then in this formula, sigma y, that would be the sum of the y column in that table that we built that I had to erase, 459. And then there's a big old honkin' square root on the bottom here. And under that radical, there's 2 brackets, which I hope you're able to see here. All right, in the first bracket, we have n again, which is the fact we had 6. Look at how many points you had, right? That's how many observations there were. There were 6 lines in the table. There were 6 students for whom we had data. Sum of x squared, what's that? What that's the sum of what color? Red, right, the x squared column was in red, 138, minus, in parentheses, sum of x, that would be that first column, that was just x, and then the formula puts a squared on that, so that'll be bracket number 1, we'll call it. Okay, then there's times. You don't really need the multiply dot, but I had to type it so that PowerPoint would pull the 2 parentheses apart. N, which is 6 again. Sum of y squared, let's see, what color is the y squared column? Oh, that's the blue one out there, isn't it? Okay, 37057. You guys have done things like this before, back when we did standard deviations and things of that nature. And then the sum of the y, 459, parentheses squared. That's the end of the second bracket. So, again, this is all from that table that we built, that you have a copy of, that I had to erase to make room for this work. All right, now if you're going to crunch this out, and again, you know how I am now with the number crunching part of this, this would just be simply the order of operations. So you would hopefully agree that we would want to figure the numerator as its own thing. We would want to figure the denominator as its own thing. And the denominator has 2 brackets, right? So I'm going to refer to them as bracket 1, bracket 2, numerator. And, okay, hit pause. Crunch the numbers yourselves if you want. I did the work ahead of time just to keep things moving. Again, hit pause if you want. Spoiler alert, I'm about to write these groups down. The numerator is negative 1590. bracket number 1, the green, if you will, turns out to be 252, and the other bracket is 11,661. And by the way, I'm going to recommend that you save those numbers because they will be of use to us later. So there we have that. And then of course you would multiply these two, take the square root of that, and then take this divided by that. So the R value here, and I want to remind you that the standard procedure for R is 3 decimal places. And so crunching the numbers here, and keep in mind these brackets had a radical over them, the square root, comes out to be negative 0.928. All right, so that's our R value. And thus far, we basically have done what would correspond to the first part of the question. So I think what we now need to do is say this will be example number 1, part A. I'm going to erase the board and make some room for some other things. Before I mention that, I'll throw out there that this does seem to be towards -1, which corresponds to the idea that that has a negatively sloped shape to it, if you will. So anyway, why don't we pause for a minute? I need to make some room. I'm going to save some of these numbers for later on, and we will continue the questions. So I will just tell you that when we return to the next video, we will then be ready to talk about example number 1 continued. We're about to do a hypothesis test to see if that R value is significant. So let's pause for a minute so I can make room on the board.